Security and privacy are an important part to consider when using IoT protocols. Each protocol at each network layer has vulnerabilities that can be exploited to disrupt, destroy, or manipulate the IoT network. The current section presents the types of attacks found in the IoT, and their target network layer. The Internet of Things virtually is a network of real-world systems with real-time interactions, usually using a three-layer communication infrastructure. Each layer and the communication between each layer is vulnerable to various attacks such as denial of service attacks, man-in-the-middle, replay attacks, and many more. The current section will introduce the types of attacks found at the Network of Things layer, and then we will discuss the application layer attacks. The Network of Things layer includes sensors and actuators that communicate with each other to monitor and gather environmental information and control the environment whenever possible. For the rest of the section, we refer to the Network of Things, as multiple smart devices communicate with each other to transmit their data to a connection device that connects the Network of Things to the Internet and the end user. We refer to the connection device as the sink. The devices may transmit data to the sink based on a predefined period or may transmit data when an event occurs. For instance, a smart home security system will only transmit data to the end user to inform it of possible home intrusion, whereas a smart thermostat application will monitor and may transmit the home temperature at predefined time intervals to ensure that the home sustains a specific temperature. The communication between the things until it reaches to the sink is what most of the Network of Things attacks aim to disrupt. There exist many attacks that target network availability by manipulating smart nodes and network communication characteristics. Each attack is customized based on the target network layer. The current table provides an overview of the main IoT attacks listed per network layer. At the physical layer, the attacks aim at the physical destruction of the device, and at the link layer they manipulate radio signals. At the routing layer, the intruder manipulates routing protocols by luring traffic towards the compromised nodes. We are going to briefly discuss how each attack is created and which vulnerabilities the attacker takes advantage. At the physical layer, the attacks take advantage of the existing physical limitations due to the size of the sensor and actuator in the smart device and/or the radio communication capabilities, and in certain cases their physical access to the device. There are two main attacks at the physical layer: jamming and tampering. Jamming attacks use radio signals to interfere with the wireless communication of the things. There are multiple versions of jamming, each varying on the transmission frequency and the packet type, but they all have as purpose to deny a sensor node executing their functionality by either denying the chance to transmit packets or by decreasing its energy. Constant jammer. The constant jammer continually emits radio signals using random bits and defies any MAC protocol with the purpose of keeping a channel occupied and preventing others from using it. The constant jammer node has the disadvantage that it is also depleting its own energy. Deceptive jammer. Unlike the constant jammer, the deceptive jammer constantly injects regular packets to the channel without any gap between subsequent packet transmissions. As a result, a normal communicator will be deceived into believing that there is a legitimate packet and will remain in the receive state, increasing its power consumption. Random jammer. Instead of continuously sending out a radio signal, a random jammer alternates between sleeping and jamming. This way it is concerned about conserving its own energy and becomes more difficult to detect. Reactive jammer. The constant, deceptive, and reactive jammer launch their attacks regardless of the track. They may only end up losing their energy without necessarily disrupting the network out. The reactive jammer is activated when it senses activity within a channel, thus targeting specific messages and disrupting the network flow. Jamming attacks can be prevented by using spread spectrum communication, cryptography, schedule switching, and error bit correction. Spread spectrum spreads the signal along a large frequency band to avoid any interference from malicious intervention. Interrupting even part of the message while in transmission may result in retransmission of the packet. Cryptography and error bit correction techniques can decrease the number of packet retransmissions as the receiver may be able to reconstruct the message. Cryptography is also used to hide the type of packet transmitted from the jammer. Another approach for preventing jamming attacks is to change the device's schedule of sleep and listening intervals in a way that the jammer cannot keep up. Jamming attacks prevention measures may make it harder for the intruder to sabotage the network of things but may cause resource exhaustion once it starts attacking the network. Tampering attack refers to the physical destruction of the device. In case a device is destroyed within the network, then flow disruption follows. This is identified as a denial of service attack, DOS, since the network's flow and the service it should provide is prevented. The smart device is no longer able to transmit or forward any data packets. Based on the location and role of the device, a portion of the network may also be affected as it can no longer transmit to the end user. Tamper-proofing the device, or make sure that it is not physically accessible to unauthorized personnel may prevent an intruder from physically destroying the node. Attacks at the link layer aim in disrupting the device-to-device communication schemes. The aim of the link layer attacks is mainly to create high resource overhead and prevent data to reach its destination. The carrier sense MAC, CSMA, protocol requires the receiver entity to acknowledge the packet once it is received. The transmitter that does not receive an acknowledgement will try to retransmit the packet. Constant retransmission of the packet deprives the device's ability to transmit other packets and forces it to be in the listening and transmitting states. The device may hold back new data packets to be transmitted until it has finally received the acknowledgement from the previous data packets. In certain cases, where the transmitter's packet storage is overflow, some packets may be lost. At the same time, the devices need to be always in the mode of listening to the channel, in case it receives the acknowledgement and constantly retransmitting the lost package. The two stages listening and transmitting have high energy consumption, and in certain applications the device, such as smartphone, will require frequent recharging. There are four common attacks when targeting the link layer: collision, exhaustion, unfairness, and interrogation. Collision attacks. The aim of these types of attacks is to disrupt the packet while in transmission to make the sender node to retransmit the packet to the receiver. Disrupting even a small portion of the packet can constitute the packet as unreadable and the receiver will drop the packet. To prevent such an attack, error code corrections are used. Exhaustion attacks. As the name implies, the exhaustion attacks aim to corrupt the last portion of the packet. The receiver node will consume computational resources by processing the corrupted packet and listening power as it waits for the retransmitted packet. Unfairness attacks is a weaker form of attacks as it deprives the right of benign nodes within the network to use the channel. One suggested prevention method is to use small frames, thus allowing the benign node to find a slot to transmit. Interrogation attacks. The interrogation attack is launched in MAC protocols that apply the request to send, RTS, and clear to send, CTS, mechanism to reserve channel access and transmit data. The RTS and CTS mechanism was introduced by the 802.11 wireless network protocol to avoid collisions. A compromised node elicits RTS messages and the targeted neighbor node will continuously respond with CTS messages. Constant transmission will again exhaust the target node's energy. The network and routing layer attacks are the most popular attacks in the network of things. The specific attacks aim in disrupting the path from the smart device to the sink. They exploit vulnerabilities at routing protocol that is being used by the network to either lure traffic towards the malicious node and to drop packets or just drop packets. They divert traffic towards the malicious device, such as never reaching their destination, denying the network to deliver the expected service. One of the attacks is the neglect and greed attack, and as the name implies, a compromised device under the neglect and greed attack acknowledges the packet received to the sender, but it neglects to forward the packet. It also classifies its own packets as of high priority to be transmitted first. Networks that use dynamic source routing, DSR, or of variations of it are more susceptible to the attack, as the sender node will determine one specific path to reach destination. The compromised node may reside along the path and the sender node may not recognize it, thus cannot divert its traffic. The effect of the attack within a network depends on the location of the compromised node and the network region size it blocks. Homing attack is a passive attack, as it requires the adversary to observe the network. The goal of the adversary is to learn the role of each node based on its location. The attacker targets the nodes that serve a special purpose within the network. They can be relay nodes, management nodes, or global security agents. The act of locating the presence of critical resources is the homing attack. Once the critical nodes are detected, an adversary can launch another attack. Misdirection attack. A compromised device node under the influence of a misdirection misleads its neighbors by producing malicious advertisements. The packets received by the compromised node will be misdirected and it will not be received by the intended receiver. The sender is denied executing its purpose and the receiver is denied receiving its packets. Preventing this kind of attack requires the use of authentication methods for the routing messages and freshness mechanism to avoid replay of old routing update advertisements. In a hierarchical structure, where there are multiple subtrees, egress filtering can be applied to the parent nodes that can examine the validity of the messages before forwarding to its children nodes. Selective forward attacks have a great impact when they infect relay nodes that are located at critical key location within the network of things. One of the goals of the relay node is to forward packets received to the correct path. A relay node under the influence of selective forward attack will select which packets it will forward, either randomly or targeting specific nodes' packets. The location of the compromised device plays a crucial role at the impact of the attack. If the location of the compromised node is closer to the sink, then more traffic will go through the compromised device, thus more packets will be dropped. A compromised node that is located at the edge of the network will go unnoticed, as no packets will forward to the compromised node for it to drop. Black hole attacks exploits the routing metrics used, such as expected transmission count, ETX, or low path cost towards the sink node, and announce to the network that the best route to choose to forward its packets is through the compromised device where another attack takes over. A compromised node under the influence of selective forward or black hole will lure nodes to transmit their packets towards it and may suppress some or all the packets. Selective forward attack on its own depends on the compromised node's location to interrupt the network's flow. Combining both selective forward and black hole attack, the impact on the network can be higher than expected. The compromised node advertises that is very close to the sink node. Once traffic is received, the node selectively chooses which packets to forward and which packets to drop. The worst case scenario is that the selective forward attack does not forward any of the packets. Sinkhole lures all nodes by maliciously advertising that it is the sink. The victim nodes transmit their packets toward the malicious node. The best location to create a sinkhole attack is near the sink, and thus get all the traffic that was destined to the sink. Sinkhole attack can either tamper with routing packets, spoof or replay route messages, or even transmit false report attacks to constitute the compromised node as a more attractive path to forward their packets. The wormhole attack is possible even if the attacker has not compromised any device, and even if all communication provides authenticity and confidentiality. In the wormhole attack, an attacker records packets, or bits, at one location in the network, tunnels them to another location, and retransmits them in the network. An infected device under the influence of Sybil attack, it illegitimately claims multiple identities. It can either steal legitimate identities from other device or create new ones. The Sybil attack can take advantage of distributed storage, or it can harm the routing mechanisms in the network of things. Prevention methods such as radio resource testing, random key distribution, device ID registration are techniques that can determine whether the packet received is from a legit node, preventing benign devices from executing any request from or transmitting to the compromised device. A compromised device that is under the influence of a hello flood attack broadcasts hello packets using a more powerful transceiver with the purpose to deceive that they are close neighbors with benign devices. A device believes that the malicious device is a neighbor node and transmits packets towards it. The packets are not received by the malicious device since the benign device's transmission range does not include the malicious device. The application layer defines the goal of the IoTs. The application layer is responsible for the data that is disseminated between the network of things and the end user application. The type of the data may vary per application. In smart home and smart thermostats applications, the data disseminated within the network may be of room temperature and control packets to regulate the temperature. At the application layer we have two types of attacks, active and passive. A passive attack does not disrupt the flow of the network or the packets transmitted, instead it violates the network's privacy. The attack's goal is to monitor and eavesdrop the network in order to gather and steal information. In the IoT, information that are personalized to everyone, such as in smart home applications, the passive attacker invades one's privacy. An active attack aims in disrupting the network's functionality and data reliability. An active attack may inject false data packets within the network and/or may compromise data by altering packets. An attack at the application level can flood the network with data messages to degrade the network's performance by causing overwhelmed traffic to the network, thus delaying the information to reach its destination or not to be delivered at all. IoT applications such as smart homes and smart thermostats, connected cars, or industrial monitoring and control applications, that rely on having fresh and accurate network information, would be less efficient if half of the information or false information are provided to the main controller. To ensure data integrity and confidentiality at the application layer, cryptography is used as a preventive measure. We have introduced the types of the attacks found in the network of things layer, and the prevention measures suggested in certain cases to avoid compromising a device within the network. Within the next presentations we will discuss the second layer of defense, the detection layer. This concludes our types of attacks in the network of things section.